Hello students, today we will do the application of the Gauss law, and this is the last portion of our chapter. We have 3 or 4 applications related to the Gauss law, and we will also see how the electric field intensity can be easily found with the help of a Gauss law. So let us move to the first application to find electric field intensity at any point due to spherical shell, that is, and hollow sphere. So first we will find out the electric field intensity at any point where our source is a spherical shell which is similar to a hollow sphere. The charges are uniformly distributed over the surface of the hollow sphere. Now when we have the source as a hollow sphere or a spherical shell, we have 3 situations. This point P can be located inside the hollow sphere, or it can be outside the hollow sphere, or it can be on the surface of the sphere. So we have 3 sub cases related to this. Now let us understand how to apply the Gauss law and what are the steps we have to follow. So first we take a spherical shell of radius capital R, and on this hollow sphere the charges are uniformly distributed. Now the charge can be positive or negative. If the charge is positive, then the field will be radially outward, and if we have a negative charge, the electric field lines will be radially inward. So this is the source given to you, that the charges are uniformly distributed over the surface of a spherical shell, and we have to find out the electric field intensity at any point. Now before we choose the any point P, let us understand this distribution. Now if you remember, this is a continuous charge distribution, and continuous charge distributions are of 3 types: linear charge distribution, surface charge, and volume charge. So this is a surface charge distribution. Linear charge distribution was 1D, 2D, and then we have a volume charge distribution 3D. Now hollow sphere is considered to be a 2-dimensional, or we have a surface charge density on it. So first we define the surface charge density for this. The amount of charge is, say, capital Q. So the first thing is to define a surface charge density. So surface charge density, which was denoted by sigma, that is charge upon area. So this is the uniform distribution, and if you remember, we have written the Gauss law is widely used to find out the electric field intensity due to some symmetry. Now here that symmetry is sphere. So if we have a proper geometrical symmetry, it is very easy to apply the Gauss law, though Gauss law does not depend on the shape and the size of the Gaussian surface that we have seen in the characteristics of a Gauss law. So here the source has a spherical symmetry. So surface charge density, the first thing is we have to define the density. So we have defined sigma is equal to Q by A, where A is the area of this hollow sphere and the area of the hollow sphere is 4 pi r square. So this is the first step, equation 1. Now we have the sub cases for this application number 1. We will take a point outside, inside, and on the surface. So let us say that first we find out the electric field intensity outside the spherical shell. So first case, point P is outside the shell. Now this is our source whose radius is capital R. The charge is uniformly distributed over its surface. Now let us consider a point P anywhere outside the cell. This is the center. Let the distance of that point is denoted by small r. So this is, the small r is a distance and capital R is the radius of the source. Now you have to find out the electric field intensity at point P. Now if you have to apply the Gauss law, the first step is take a Gaussian surface in such a way that the charge is enclosed inside it, or the point P comes on the surface of the Gaussian surface. So this is an imaginary concept. So we assume a spherical Gaussian surface. This is shown by the dotted line. So this dotted line is an imaginary Gaussian surface whose radius is small r. So Gaussian surface radius is small r and point P is lying on the surface. So this is the first step. First step we have defined the density. Now we have to find out the electric field intensity outside the cell. So we have taken the point P whose distance from the center is small r. Now we have taken the Gaussian surface. This is a spherical Gaussian surface and the point P lie on its surface, on this surface. Now electric field lines are radially outward. So we have a Gaussian surface of radius r and r small r is greater than the capital R, means we are outside the cell. Now we divide this entire Gaussian surface into the small elements, Gaussian elements say. So I take this small element, this is one element, this is another element, this is another, like this. We have done this in Gauss theorem or Gauss law. So these are the elements. Now the direction of the electric field intensity through this Gaussian element. So this is Gaussian surface. And now I am considering one element. So area vector that will be radially outward. Let us denote it by delta S. Now since the charge is positive, the electric field line is also radially outward. So this is E vector. Now here this Gaussian surface has a symmetry, means if I take any point, say this was a point P, this is say another point, say the point is S. Another point, say the point is X. All this point will be at the same distance small r from the center. So the electric field intensity at all this point will be same. So we call it a proper symmetry. Now for this Gaussian element, the electric field intensity and area vector are in the same direction. So after doing this geometrical portion, we find out the flux linked with this small element. So let delta phi be the electric flux linked with Gaussian element of area delta S vector. So delta flux or delta phi is equal to, now the definition of flux, that was E dot delta S. Here both are in the same direction, so angle is 0. So it becomes E delta S cos of 0, that is 1. So we have E delta S. Now this is equation 1, say this is equation number 2. Now this is the flux which is linked with a small element. Now we want to find out the flux linked with entire Gaussian surface. So we sum up this or we do the integration. So the total flux phi is equal to summation of delta phi. Now if this area element delta S tends to 0, then I can take the integration also. So we are summing up for all delta S. So this is equal to E summation of all the elements delta S. So delta S, delta S, delta S, delta S. So area of the entire Gaussian surface, that is equal to 4 pi r square, small r square, that is 4 pi r square is the area of this Gaussian surface. So this is the flux linked with the entire Gaussian surface or outside the point, at a point outside the spherical shell. This was our source. So according to the definition of flux, this is the formula. Now we apply the Gauss law. What Gauss says? According to Gauss law, flux is equal to summation Q upon epsilon naught, that is the total charge enclosed. Now the total charge enclosed, if we see the diagram, the entire charge is enclosed inside the Gaussian surface. Entire charge was taken as capital Q. So flux is equal to Q upon epsilon naught. The entire charge comes inside the Gaussian surface. Now we need to find out the electric field intensity. So we compare equation 3 and 5. So comparing this equation, at the same time we need this equation 1 also. So equation 1 is sigma is equal to Q upon 4 pi r square. Now I compare equation 3 and 5. So comparing equation 3 and equation 5, E 4 pi r square is equal to Q upon epsilon naught, and therefore the electric field intensity is Q upon 4 pi epsilon naught r square. Now if you remember, this is what we have, the electric field intensity, if your source is a point charge. Here the source was a spherical shell. Now even if we have a point charge Q, the formula comes out to be same. So 1 upon 4 pi epsilon naught is K. So this can be written as KQ upon R square. So this is the electric field intensity outside the spherical shell. So that is E is equal to KQ upon R square, or it is Q upon 4 pi epsilon naught R square. So this is your final result for R greater than the capital R, that is outside the cell. Now this diagram, like in 11th we have a center of mass. The entire mass of the body was assumed to be concentrated at its center. So if I want to draw the equivalent diagram for this, we assume the entire charge of this source, which was a hollow sphere, is assumed to be concentrated at its center. So this is our, again, the Gaussian surface. This is plus Q, and this distance now becomes smaller. So we have assumed that this hollow sphere have a charge which is concentrated at its center. Now this is our point P. So our formula becomes KQ upon R square. Or even if we have a point Q charge, and if I take a point P at a distance R, then also the formula comes out to be same. So whether your source is a hollow sphere or it is a point charge, the answer comes out to be same. The electric field intensity remains same because the entire charge is assumed to be concentrated at its center, and therefore E is inversely proportional to the square of the distance of a point from the center. So these are the equivalent diagram. Even if I take a point charge, it depends on the magnitude. If you remember the characteristics of electric field intensity, the electric field intensity depends on the magnitude of the source charge. So we assume that instead of a continuous distribution, we have entire charge concentrated at its center, or we have a point charge of same value. So our formula in any of this case becomes kq upon r square, that is E is inversely proportional to the square of distance. Also, the electric field lines are radially outward. This is the electric field lines radially outward. We have a source positive. So in vector form, E vector can be written as kq upon r square, r cap. This is what we have a derivation for this point charge when we have introduced the concept of electric field intensity. Here r cap is unit vector radially outward if Q is greater than 0 or sigma is greater than 0, if the surface charge density is positive, and inward if Q is less than 0, that is if our source charge is negative. Now this is the formula in the form of the source charge. Now sometime if surface charge density is given, we substitute this Q as sigma into 4 pi r square. So substituting equation 1 in E is equal to kq upon r square, we write E is equal to, now in the place of k I am writing 4 pi epsilon naught. Q can be written as sigma into 4 pi r square upon r square. So this 4 pi get cancelled. So another form of this equation is sigma r square upon epsilon naught r square, where r is greater than the capital R. That is, we are outside the spherical shell. If it is equal, in the same derivation, if I take the point on the surface, then in the place of small r I can write capital R. This r square get cancelled. So I will get sigma upon epsilon naught. Or here, if it is equal, so now I am writing the equal sign. Even if this point is on the surface of the spherical shell, small r should be replaced by capital R. So your formula becomes kq upon capital R square or sigma upon epsilon naught. So this is the electric field intensity outside the spherical shell. Now this was the first sub case for our hollow sphere. Now let us take the point inside. Now the second part is find electric field intensity inside spherical shell. So now again we take a source. Source was the hollow sphere on which the charge distribution is taken as a positive. The radius was capital R. This is the center, and Q amount of charge was deposited on the surface. Now we have to take a point inside the spherical shell. So I take a point inside this. Now when you have to apply the Gauss law, first step is to imagine a Gaussian surface. So let us consider this as an imaginary Gaussian surface. Its radius become small r. So small r is the radius of the Gaussian surface. Now this is your Gaussian surface. And small r also become the point P distance from the center. Now the second step is we divide this Gaussian surface into the small element, that is a Gaussian element. So I take again one element, area vector normal to the surface or radially outward, that is delta S. Now electric field intensity, because the charge are uniformly distributed over the surface, the field lines will be radially outward. So there is no field line passing through this Gaussian surface or Gaussian element. So by common sense also it is clear that you are inside the spherical shell and none of this field line will pass through this Gaussian surface. So the electric field intensity inside the spherical shell should be 0. But let us apply the Gauss law and see whether this electric field intensity is 0 or not. So again we use the definition of flux. You see this method, first you have to apply the definition of the flux and second part you apply the Gauss law and then you compare the equation. So we know flux can be written as, now I am directly writing the total flux, that is equal to E delta S, E summation of delta S. So we take a summation for all of this Gaussian element and that is equal to E 4 pi r square. So the total flux, this is say our equation number 1 for this, say equation number 2. This is your common equation for all the derivations. So the flux taken for entire surface is E 4 pi r square, where delta S is the area of this small element. So delta S, delta S, delta S. So entire Gaussian surface area is 4 pi r square. Now we apply Gauss law. According to Gauss law, flux should be equal to summation q upon epsilon naught. But what is summation q? If you remember the Gauss law, we have to take only those charges which are enclosed in the Gaussian surface, and none of this charge is enclosed in the Gaussian surface. Here summation q is equal to charge enclosed in Gaussian surface and its value is 0 because all the charges are on the surface of the spherical shell. So substituting this value, the flux link becomes 0. That is equation number 3 say. So first we apply the definition, then we apply the Gauss law, compare this equation. So comparing equation 2 and equation 3, E 4 pi r square is equal to 0 and therefore E is equal to 0 for r less than capital R. So anywhere inside the spherical shell, the electric field intensity comes out to be 0. So if I say the radius of the spherical shell is 5 centimeter. So for all points at distance less than 5 centimeter, the electric field intensity is 0. So if I am 1 centimeter away from the center or 2 centimeter or 3 centimeter, whatever be the value less than 5 centimeter, the electric field intensity is 0. So for outside, we have kq upon r square, that was inversely proportional to the square of the distance of a point P. And in this case, the electric field intensity comes out to be 0 whether the surface charge density is positive or negative, because either the field line will be radially outward or inward, but it will not enter inside the spherical shell. We will see its use in chapter 2 also. So for the time being, if you are inside the spherical shell, the electric field intensity is 0. Third portion. Find electric field intensity on the surface of spherical shell. Now if you are on the surface, small r is equal to capital R. So instead of doing the entire derivation in first part when we were outside, so wherever we got the value small r, we substitute capital R. And the diagram, a little change in the diagram. So this is, the charge is uniformly distributed over the surface of the hollow sphere. Capital R is its radius. Now point P is lying on it. So this distance becomes small r. Clearly capital R is equal to smaller. And I draw this Gaussian surface. So this hollow sphere itself become the Gaussian surface. Now again I take a small element. Now I take this delta S. The field lines is radially outward. So first I apply the formula. Now I am writing total flux. You have to find out flux for a small element. Then you do the summation directly. It becomes E 4 pi r square, because small r is equal to capital R. So this becomes our equation 2. Now Gauss law says flux is equal to summation q upon epsilon naught. So all the charges are, in the first case it was enclosed inside, or now all charges are on the surface. So that is q by epsilon naught, say equation number 3. I compare both these equations. So E 4 pi r square is equal to q upon epsilon naught. So E is equal to q upon 4 pi epsilon naught r square, which can be written as kq upon capital R square, where small r now is equal to the capital R. So this is the derivation when point P is on the surface. And instead of writing all this thing in the first part, we substitute capital R in the place of a small r. So either it becomes kq upon r square, or if I make the use of this equation 1, in the place of capital Q I write sigma upon 4 pi r square, I get E is equal to sigma upon epsilon naught, where your R is equal to capital R. So this is the first application of the Gauss law, where the source was a spherical shell and the charge was uniformly distributed over its surface. So you see the steps. It becomes very easy to find out the electric field intensity using the Gauss law, but it will be easier if you have a proper geometrical symmetry. For example, we have here the sphere, so it is easier to put this area of the Gaussian surface. If we have an irregular shape, we can use the Gauss law. The answer comes out to be same, because Gauss law does not depend on the shape and the size of the Gaussian surface. But for derivation, we need a proper geometrical shape. So this is the first application of the Gauss law. So if we sum up all this thing with the help of a graph, now let us see how the graph of this E versus the distance of point P can be drawn. Now let us write this. For outside, E is equal to kq upon small r square, where you have to remember small r is the radius of the Gaussian surface, or it is a distance of point P from the center. So this is the derivation. Again I am saying it is outside the spherical shell, or the same formula we get if our source is a point charge. So outside, this was a formula. Second, inside is 0 because no charge is enclosed inside the Gaussian surface, and on surface E comes out to be kq upon capital R square, where R is equal to R. Now let us plot the graph. This is small r E. So if you are inside the Gaussian, inside the spherical shell, the electric field remains 0 till you come on the surface. So from at the center, I am at the center. This was our source. ये source था अपना. Capital R was its radius. So let us say capital R is 5 centimeter. Now for all the points inside it, means say let us say point P is 1 centimeter away, 2 centimeter away, 3 centimeter away, 2.5 centimeter away. All the points comes inside it. For all that small r values, E is 0. So as the distance increases from the center till we get to the surface, the electric field remains 0. So this is the electric field intensity. 0. So we darken this portion. Now I reached on the surface. So on the surface, the electric field intensity increases, and outside E is inversely proportional to 1 upon R square. So it will decrease. So inside it is 0. On the surface, it becomes maximum. So this is the value on surface. I am writing ES, S for surface, and this is small r is equal to capital R. So suddenly the field increases, and this is its value, a constant value, because this can also be written as sigma upon epsilon naught. Now if I move outside this, say 6 centimeter, 7 centimeter, 8 centimeter, the field decreases. So this remains constant, and this is inversely proportional. So E is inversely proportional to the distance of a point, square of the distance of a point from the center, and on the surface this is its value, and inside, let us denote it by dotted line only. So this is the value at the surface, ES. So on y-axis we have electric field intensity, and then it decreases rapidly as we move away from the spherical shell. So this is what we have for today's lecture. This is the first application. We have 3 applications. So we will do another application in the next lecture also. So we complete our today's lecture at this point. Have a good day.